Hi, this lecture is the continuation of our previous two lectures related to the two random variable or bivariate random variables. So this lecture I have prepared on students' demand. In this lecture, we will discuss few problems related to the conditional probability mass function and conditional probability density function. So the conditional probability mass function is related to the discrete random variable, or the case of bivariate random variable, discrete bivariate random variable, and the conditional probability density function is the case for continuous bivariate random variable. So in previous two lectures, we have talked about bivariate random variable for both discrete and the continuous cases. Further, we discussed about the joint probabilities and its probabilities, then the marginal probabilities. Moreover, we have talked about the independent random variable for both discrete and continuous cases. Also, we have solved a few problems related to joint probabilities or marginal probabilities as well as conditional probabilities. So in this lecture, I will discuss we will discuss few problems. Those are related to the conditional probability mass function as well as conditional probability density function. So let us talk about first talk about the conditional probability mass function. If bivariate random variable is x and y is a discrete bivariate random variable with joint probability mass function, which we define p sub x y of x and y, and then the conditional probability mass function of y given x, capital X is equal to small x, is defined as probability of y. This sign is used for this bar. I mean, this bar is used for we say it given y given x is equal to the joint probability of p sub xy divided by the probability of x, or the marginal probability of x, we can say. In similar fashion, the conditional probability of y can be find the joint probability of x and y divided by the conditional probability of y. Here is the properties of the conditional probability mass function. So it could be greater than or equal to 0 and could be less than or equal to 1. It range from 0 to 1. Similarly, by taking the summation, all sum of the conditional probabilities would be equal to the 1. Now, taking into account the conditional probability density function, so the conditional probability density function we use for continuous random variable, bivariate random variable. If x and y is a continuous bivariate random variable with joint PDF, in this case we use the small f sub xy of xy, then the conditional probability density of y is given that x, capital X is equal to small x, is defined as the probability PDF of y given x. This bar is used for given x is equal to the joint PDF of x and y divided by the marginal PDF of x, such that f sub x is greater than 0. Similarly, the conditional probability density function for x given y is defined as the joint probability of x and y divided by marginal probability of y. Further, the properties of conditional PDF as follows. The conditional PDF could be greater than or equal to 0 by integrating the conditional PDF from minus infinity to infinity. So the conditional PDF of y given x, if we integrate it from minus infinity to infinity, it must be equal to the 1. So now let us solve or discuss a few problems related to the conditional probability mass function and probability density function. Consider the binary communication channel. So the fig is shown here. So here is the binary communication channel. This is random variable x, this is the random variable y. This could be a random variable x, could be a 0 or the 1. Similarly, the y have possible value 0 or 1. So there the probability, conditional probability of y equal to 1 equal to 0 given x is equal to 0. Similarly, there are the 4 possible probabilities are given here in this channel. So let us discuss about this problem. This problem is already we have talked about, in our textbook. This is related to the problem 1.52. Let xy be a bivariate random variable where x is the input to the channel and y is the output of the channel. Thus x random variable define the input of the channel and a random variable y define the output of the channel. Let probability of x equal to 0 when x is equal to 0 is 0.5. Similarly, the probability of y equal to 1 given x is equal to 1 is equal to 0.1. So we can say when x is equal to 0, the probability that on the output channel the output you will get 1. So this is equal to 0.1. You can say the probability of error. So this is 0.1. Similarly, the probability y is equal to 0 when x is given x is equal to 1 is equal to 0.2. So first we have to find the joint probability mass function of the bivariate x and y. Next, find the marginal PMF probability mass functions of x and y. Are x and y independent? So let us talk about the first case in which we have to find the joint probability. In problem 1.52, we have given that the probability of x is equal to 1, that is equal to 0.5 or 1 by 2. Similarly, the probability of y equal to 0 given that x is equal to 0, that is equal to 0.9. So we can say the probability of success when you transmit x is equal to 0, you will get on the output y is equal to 0, its probability is 0.9. Similarly, when you transmit x is equal to 1, it means the probability of y is equal to 1 given x is equal to 1. This is 0.8. So here the joint probability is when the probability of x is equal to 0, y is equal to 0 is equal to, we can write it as the probability of y is equal to 0 given x is equal to 0 into the probability of x is equal to 0. So we have already derived this formula. So in this case, the probability, conditional probability y is equal to 0 given x is equal to 0 is 0.9. The probability of x is equal to 0 is 0.5. So their product will be the 0.45. So this is the joint probability of when x is equal to 0 and y is equal to 0. So similarly, the joint probability of x is equal to 0 and y is equal to 1. So in the same way, we can find out the joint probability which is equal to 0.05, and the probability of x is equal to 1 and y is equal to 0, that is equal to 0.1. So this is the joint probability when x is equal to 1 and y is equal to 0. For x is equal to 1 and y is equal to 1, this is 0.4. So we can write their joint probability of x and y. For x is equal to 0 and y is equal to 0 is 0.45. The joint probability of x is equal to 1, y is equal to 0 is 0.1. Similarly, the joint probability of x is equal to 1 and y is equal to 0 is 0.4. So next we have to find the given in problem, we have to find the marginal probability mass functions of x and y. So in this here, the marginal probability mass function of x is defined as so in this formula we have two possibilities. When x is equal to 0, then the output in this channel, the output could be a 0 or 1. So the joint probability when x is equal to 0 and y is equal to 0, we have already find out, that is 0.45, and the joint probability of x is equal to 0 and y is equal to 1, that was 0.05. So the total marginal probability mass function for x is equal to 0.5, and similarly we can find the marginal PMF of x is equal to 1, that is a 0.5. The marginal, in similar fashion, the marginal probability mass function for y is equal to 0, that is, there are two possibilities. X could be here, x could be a 0 or 1. When x is equal to 0, their joint probability is 0.45. We have already found out in part A. And when x is equal to 1 and y is equal to 0, their joint probability was 0.1. So the marginal probability of y is equal to 0 is 0.55. Similarly, the marginal probability of y is equal to 1 is 0.45. This is the communication channel. So the channel, when we transmit 0, it could be a 0, it could be a 1 at output. When we transmit x is equal to 1, could be a 0, and the higher probability is it could be a 1, and lower probability because of noise it could be a 0. So in the third part, we are x and y are independent. So here the probability of x equal to 0 and y is equal to 0, the probability of y is equal to 0 is point their product. When we'll take their product, this is 0.275, which is not equal to the joint probability of x and y when x is equal to 0 and y is equal to 0. So we can say that x and y are not independent. Next, move to another problem. We consider we have a bivariate random variable x and y with joint probability mass function s. When x is equal to 1 or 2 and y is equal to 1 or 2, range 1 or 2, so this is the joint probability of x and otherwise it is 0. So here we have to find their conditional probabilities. So first let us talk about random variable x. We have to find its marginal probability mass function of random variable x. So from this formula, so x could be a 1 or could be a 2. So when we will incorporate here x is equal to the marginal probability mass function of x, so it could be a y could be a 0, y could be a 1 or 2. So here I will incorporate in this formula first y is equal to 1 over 18 into 2x plus y. When y is equal to 1, I will expand this formula. When y is equal to 2, when I will sum up, I will get 1 over 18 into 4x plus 3. So similarly, the marginal probability mass function y, we can find out there could be two possibilities. X could be a 1 or x could be a 2. When x could be is a 1, I will get this term. When x is equal to 2, I will get this term. By adding these two terms, I will get 1 over 18 into 2y plus 6. So next, I have to find the conditional probability of y and x. So the conditional probability of y given x. So the formula is the joint. Here I will write the joint probability of so I can write it as the joint. Here there would be a joint probability of x and y. This formula is equal to the joint probability would be x comma y and what I will do here, I will divide this I will divide this with the marginal probability of x. So this is equal to the conditional probability of y. So here we know that the joint probability of x and y was 1 over 18 into 2 of x, 2 into x plus y. So I will divide it with the marginal probability of x, which is 1 over 18 into 4x plus 3. So by dividing joint probability with the marginal probability of x, I will get this formula. So similarly, the conditional probability of this is the conditional probability of y, and this is the conditional probability of x. The probability of x given y, in similar fashion I can find this. So the next part, when the condition in this problem, the condition was given y is equal to 0 given that x is equal to 2, y is equal to 2 given that x is equal to 2, I will get this. By incorporating in this formula, I will get. So probability of y is equal to 2 given x is equal to 2, we will incorporate in this formula. So I will get the probability 6 by 11. Similarly, the probability of x is equal to 2 given y is equal to 2, so I will incorporate in this formula. I will get 3 by 5. So let's move to next problem. So in this problem, consider a random variable, bivariate random variable xy with joint PDF given as. So here is the joint PDF of two random variable x, and when x is greater than 0 less than 2 and y is greater than 0 less than 2. So this is the joint probability of x and joint PDF of bivariate random variable xy, and it is equal to 0 otherwise. So find the conditional PDF of y given x and the conditional PDF of x given y. In the next problem, we have to find the probability of y is greater than 0 less than 1 by 2 given x is equal to 1. So first let us talk about the marginal. We have to know the marginal PDF of x and y. So the marginal PDF of x, I will integrate this formula, this joint PDF from minus infinity to infinity. I will integrate along yx for y variable. So by integrating this uh, this random variable y from minus infinity to infinity, so I will get so again the given limits for y is from 0 to 2, so I will integrate it from 0 to 2, so I will get, eventually I will get this condition marginal pdf of x is equal to 1 over 4 into x plus 1 when x is greater than 0, less than 2, otherwise it is equal to 0. Similarly, the marginal pdf of y, what I will do, I will integrate this bivariate joint pdf of bivariate random variable from along x variable. So when I will integrate it, so from 0 to 2 along by integrating along x-axis or along x variable, so I will get the marginal pdf of y, which is equal to 1 over 4 into y plus 1. So after getting the marginal pdf of x and y, so I can easily find out the conditional pdf of y as well as x. So what I will do to find the conditional pdf of y, I will take the joint pdf of x and y, I will divide it the marginal pdf of x, so then I will get the conditional pdf of y. Similarly, the conditional pdf of x, I can get it by dividing the joint pdf with the marginal pdf of y. So here by doing this I will get the conditional pdf of y given x, which is equal to 1 over 2 into x plus y divided by x plus 1. The condition is when x is greater than x and y are greater than 0 and less than 2. Similarly, I can find out the conditional pdf of x given y. What I will do here on the numerator, I will take the joint probability of x and y divided by the conditional marginal probability of here I will take the marginal probability of y. So here this is my conditional probability of x given y. The next, in the p part, what I have to do, we have to find the probability of y when it is greater than 0, less than 1 by 2, given x is equal to 1. So x is equal to 1, which is given, so I will integrate this conditional this conditional pdf of y. I will integrate it from 0 to 1 by 2 when x is equal to 1. So I will incorporate it, x is equal to 1, so I will get the formula here. I will get 1 plus y divided by 2. So when I will integrate it along y direction or for y random variable, I will get the answer would be equal to 5 by 32. So another problem, let us talk about another problem. We have to find the conditional pdf of y given x and the conditional pdf of x given y for the bivariate random variable x and y. The problem we have already discussed, 3.18. So in this problem, the joint probability of x and y is equal to 4xy when x is greater than 0, less than 1. Similarly, y is greater than 0 and less than 1. Otherwise, it is 0. So here is the marginal pdf of x, which is equal to 2. So how already we know that we can find the marginal pdf of x. What we will do is joint pdf, we will integrate it from 0 to 2 for random variable y. So I will get the marginal PDF of x. Similarly, for the marginal PDF of y, I will integrate this joint PDF from 0 to 1 for random variable x. So I will get marginal PDF of y is equal to 2y. So next, for conditional PDF of y, what I will do, this joint PDF of x by bivariate random variable x and y, I will divide it with the marginal PDF of x. So I will get this is equal to 2y. The condition is y is greater than x and y are greater than 0 and less than 1. Similarly, the conditional PDF of x given y, which I will find it, I will divide the joint PDF of x and y with the marginal PDF of y. So I will get this is equal to 2x. So again, note that f conditional PDF of y given x is equal to the marginal PDF of y, and the conditional PDF of x given y is equal to the marginal PDF of y of x, as must be the case since x and y are independent. So in this case, x and y are would be the independent random variable. So that's it. In the next lecture, we will talk about the covariance and correlation coefficient. Thank you.